last time, we defined the single particle potential operator in many body system. So today we will continue doing this by defining this kinetic energy and two particle interaction potentials in many body system. But before we do this, let me just go back a little bit. Definition of the single creation destruction operator, and there's a very important operator called the number operator, which I didn't define, or I defined, but I have not proved that the number operator is indeed working as a number operator. So the number operator defined by the C dagger PCP, where this dagger representing the creation operator is put on the left-hand side of the destruction operator, CP, where the CP is on the right-hand side. Okay, so this order is very important because if you switch the order, and this is not the number operator anymore. Okay, so CP dagger is not the number operator. Okay, so why is this number operator? Well, because if I use this number operator and add this operator onto the occupation number states MP, where MP stands for the occupation number and for state P. Okay, meaning if P labels some quantum number such as momentum position, this says that there's a particle number MP in state P. Okay, so if this is the case, then this number operator, when acting on this MP state, gives you the eigenvalue MP, which is precisely the number of particles in state P, and multiply by the MP state. So this is the eigenvalue equation. So follows from the quantum mechanics. If this MP is the MP state is the eigenstate of this operator MP, and this eigenvalue equation must be satisfied. Indeed, it will satisfy, and let's check. So if I spell out the number operator MP in terms of a C dagger PCP, and I use that operator and act onto the state, MP equals to 1, and all the other states I don't care. So following the same definition that we already defined, we could carry out these two calculations, two operations. The first one is to destroy the particle in state P by a CP operator, which can be done by the standard definition of a CP. The resulting answer is -1 power of capital MP, and you have this one creation operator remains, and multiplied by this state MP equals to 0, because initial state is the single particle state. By destroying that single particle, the final state is empty state. Okay, so this is just the first step. The second step is you need to create a single particle at the state P. Once again, then you could just plug in this definition of the CP dagger, and you get another factor of -1 power of MP, and multiplied by this occupation number MP being 1, which is increased by 1 from the empty state. So you simply multiply this 2 minus factor, so -1 to the power of MP plus MP. So whatever MP is, I don't care, is 2 times MP, which is an even number. So -1 times -1 is actually +1, okay? Or -1 to the power of 2 MP is an even number in the exponent. Therefore, you multiply even number of times the -1, which gives you +1 times the original state. So if you look at this prefactor, naive looking as it sounds, but this is non-trivial because this prefactor +1 is precisely the number of occupation you have in the beginning, right? So this +1 refers to the fact that occupation for the initial state MP is 1. So I can simply just rewrite this as, this prefactor is MP times this state MP equals to 1. But this is just one special case where you have a single particle here, so the number is actually plus 1, so it sounds trivial and simple and very naive, but let's try another state. So if this initial state MP is actually 0, there's no particle in the state P initially, and if you apply this MP operator, that state, it will give you 0 because you cannot destroy the empty states anymore, right? From the definition of the destruction operator, and therefore you get 0, but 0 is actually 0 times this initial state. Okay, so the prefactor 0 is nothing but the occupation being 0 in your initial state. Okay, so in these two cases, I checked that this eigenvalues are precisely the number of particles in your initial state. Okay, and therefore this is checked that this eigenvalue represents the number of particles in your eigenstate. Okay, and that's why you call this operator number operator, because the eigenvalue is precisely the occupation number in that state. Okay, if you use that operator. And later, for bosonic system, there are more than just two possible states, occupation number being 0 and 1, so you get occupation being, say, 0, 1, 2, 3, 4 until infinity. And later we will show that, again, this occupation number operator, when acting on this occupation number states, gives you the eigenvalue, which is precisely the occupation number. Okay, so we will wait for later part when we define the bosonic creation and destruction operators. Good. So now let's check again this anti-commutation rules that we mentioned last time, since we just mentioned this number operator. So again, remember last time we have this CI CJ dagger with anti-commutator. This is delta ij, right? Which means that this is 1 if I equals to j, and 0 if I is not the same as j. Okay, so let's check when I equals to j. When I equals to j, this is nothing but this sum of these two terms, C dagger P CP plus CP CP dagger. And the first operation, C dagger P CP, this is nothing but a number operator that we just defined over there. So as I mentioned, C dagger C plays a different role as C dagger. Okay, so if you use C dagger C for this operation, you get this eigenvalue 1 multiplied by the state, MP equals 1. However, if you switch the order, so if you use the CP dagger as an operator acting on the same state, you get 0. Because for fermions, you cannot create a double occupancy, right? Because there are at most one fermion occupying any quantum states. There cannot be two fermions occupying the same state. So this operation gives you 0 right away, so you can see clearly that the first result is not the same as the second result, right? And therefore, C dagger C plays a different role as CC dagger, because when you apply both operators to the same initial state, you get different answers, right? Okay, but if you add these two, 1 and 2, and acting on the same states, you get 1. Because 1 plus 0 is actually 1 times the same state. And now the state, initial state, could be arbitrary, so it doesn't necessarily, it doesn't have to be the state. You could have a different state, such as MP equals 0. In boson system, this MP could be arbitrary, and therefore you get the conclusion that if I calculate this commutator of CP and CP dagger, where this P is the same as that P, which gives you 1. Okay? And then this is your part of homework problem. Okay? But in general, if P is not the same as P prime, here that the states for the creation operator is different from the states for the destruction operator, and you assume that this state P is different from state P prime, and use an arbitrary, say, NP equals to 1 and NP prime equals to 1 state as the initial state, and again you perform such operations for CP dagger CP prime and CP prime CP dagger. Okay, and then you add them together, you get 0. Okay, so that's part of your homework. So I suppose that everything you need to know regarding the single particle creation and destruction operator have been introduced already. By the way, so everyone should know that this year's Nobel Prize in Physics was just announced yesterday, and this is the kind of a special homework. Why do you need to do this homework? The reason is simple, because the topic of this year's Nobel Prize in Physics is about the magic and the power of quantum mechanics. So the heart of their work, the key point of this 3 experimentalists' work was the confirmation of a quantum entanglement. Okay, so meaning if I have a singlet state, just like a 2-spin 1/2 system, if this electron state is in the singlet state, then you know from quantum mechanics that the spins of these 2 electrons are correlated in this state, that if this electron number 1 carrying spin 1/2 and electron number 2 should carry spin down and vice versa. It's called quantum entangled state. Okay, so these 3 gentlemen and great experimentalists designed techniques and their experiments to check that indeed, if one electron is carrying spin 1/2, another electron should carry spin down. Okay, if they are in the singlet state. Okay, and no matter how far they are apart from each other, so this kind of up and down correlations should be respected, and they have checked that indeed it is respected. And what we are doing here is the generalization of a single particle quantum mechanics to many-body solid state. But the principle is the same. It's just a collection of many single particle quantum mechanical states. Okay? And many very fancy quantum technologies such as quantum information, quantum computation, and quantum teleportation, and quantum computer, and so on and so forth. These technologies are all based on this principle of quantum mechanics, which is the quantum entanglement and also superposition of the quantum states. Say if there is a state called gamma, and we could make linear combinations of 2 quantum mechanical states, alpha and beta, with different probability amplitude, and if I make such combinations, it consists of a different quantum mechanical states. And therefore, the different quantum states could be linearly superimposed, and that's the fundamental principle of quantum mechanics. So these 2 principles are the building blocks of all this quantum technology. And therefore, I think it is an important lesson that you need to learn. Why are these 2 principles valid? Okay, so how to prove and how to appreciate this seemingly counterintuitive statements or phenomena, but these are not science fictions, but they are reality. So they prove that these 2 statements are correct, and it is scientifically rigorous statements and could be reproduced. Okay, and similarly, what we are doing here is the application of a single particle quantum mechanics to many body system, where each of the single particles satisfies these 2 fundamental principles of quantum mechanics. So not only can we have such a fancy quantum technology, but quantum mechanics, if you describe many different quantum particles that they are interacting with one another, and new quantum mechanical phenomena will arise. And this is precisely what we are talking about in this course, that quantum many-body phenomena in solid-state physics. So, in other words, the magic and power of quantum mechanics, still pretty alive and really powerful and fascinating. And the importance of this quantum mechanics has been demonstrated by this Nobel Prize in physics for this year. All right? So what we are learning and studying here is very important, at least for fundamental reasons and also for fancy applications. Okay? So that's the some kind of extra homework. You could write a one-page summary of what they have done, the three experimental physicists, and the significance of what they have done. Okay, so let's take a short break. When we come back, we will continue defining the single particle potential in many-body state and also two-body interaction in many-body states. Great. So last time we defined single particle potential in many-body state, system. In the same way that we defined our single particle operator. Okay, so you could use a cartoon picture to illustrate this single particle scattering in many-body states. So in this kind of cartoon picture, that you have many single particles, right? Like ions or electrons. Okay, but you consider just a very simple, the simplest possible potential, where you just have an on-site potential, which affects only the particle number I, the ith particle, and it doesn't care about all the other particles. This is the simplest possible example of this potential term, like impurity potential or random potential. Okay, so you can imagine that I have some initial states, and the states describes a single particle, and that single particle gets scattered by a potential right here, and then after scattering, there's different states of that particle emerges. Okay, and there are many such single particle potential in real space, and you need to sum over all such a single particle potential, but this potential only affects the initial and final state of a particular particle in particular position, say I. Great, so you could simply interpret this kind of a single particle scattering as you destroy initial states of a single particle, say state alpha I prime, and by scatter this with the potential with a strength VII prime, which is the matrix element of this potential for the scattering, and after scattering you create another particles carrying this quantum number alpha I. So you destroyed a single particle alpha I prime, and you create another one at alpha I. Okay, and this scattering amplitude is precisely this matrix element VII prime, which is the expectation of this operator V sandwiching between the initial and final state. This is the scattering amplitude, and that's it. Okay, and you sum over all possible this alpha I and alpha I prime, and end of the last lecture mentioned that the alpha I state could be very conveniently represented by the momentum eigenstates, or the eigenstate of a momentum operator, which says that the P operator acting on the, say, state P or state K, gives you this eigenvalue, which is the momentum itself, the magnitude of the momentum multiplied by the states. Okay? So in many cases, the momentum representation of the scattering potential is actually very useful and convenient. So we will take advantage of such convenience for later purposes. Good. So that's the single particle potential in many body state. And let's just review the kinetic energy that I already mentioned last time. In the first quantization, in the single particle Schrödinger picture, this is simply just second derivative of your wave function respect to your spatial coordinate multiplied by this prefactor. But last time we have shown that this is nothing but this form in second quantized formulation, where C dagger K, CK refers to, again, a number operator for electrons or for fermions that populated in state K. Okay? And you know very well that this N of K is nothing but the Fermi-Dirac. If you take the expression value of this number operator, this precisely tells you the probability or the number of your electrons in state K. And this is the reason why we need to count the particle number, because we know already that the expression value or thermal average of this occupation number operator is nothing but the Fermi-Dirac distribution or Bose-Einstein distribution for fermion and boson systems respectively. And in this fermionic systems, this ensemble average of NK operator is precisely the Fermi-Dirac distribution. And this second quantized formulation of the kinetic energy simply tells you that you need to sum over the average kinetic energy per particle or per electron multiplied by number of electrons, right? So that's precisely what this tells you. The total kinetic energy of your electronic system or free electrons consists of this summation over all possible or occupied state K, where in that summation you simply just calculate the number of electrons times the average kinetic energy per electron. So that's the total kinetic energy for a state K, and you sum over all possible states. So that's your total kinetic energy. And imagine that you consider the momentum eigenstates as your initial and final state for potential energy operator. You could simply just re-express in terms of such a summation, and such a kind of a momentum space representation of the single particle potential in many body states could be rigorously derived by Fourier transform of the real space potential. So we will sort of provide you with more details just a moment. Okay, so V of R is the real space representation of this potential energy, and the VKK prime is the matrix element of this potential operator in K space, which is the expression value of this V operator sandwiched in between these two momentum states, K and K prime, to the left and to the right. Okay, so we will sort of establish such a relation between the real space and momentum space operator in just in next lecture hour. But this is just the relation I just wrote down here first. So if you sum over these two terms, the potential energy for a single particle potential and kinetic energy for free fermions, and you get this Hamiltonian, which is the simplest possible form of a many-body system of electrons. Okay, so if we don't consider the Coulomb interaction, but we will consider Coulomb interaction in just a moment, but just the kinetic energy of free electrons and the single particle potentials energies in the momentum basis, and the sum of the two constitutes the simplest possible Hamiltonian for a many electron system. Okay, just free electron gas plus a single particle, say, impurity potential, that kind of a term, but in the second quantized form. Okay, so later we will generalize or expand this Hamiltonian to include the two electron Coulomb potential and so on. Okay, but you could see that we could literally count the particle number from this Hamiltonian. Okay, so this is nothing but electron number operator. But what about this? Well, again, we should interpret this potential scattering as the destruction of initial particle and the creation of the final state particle. So it's again, you destroyed a particle and you create another one. Okay, so all pieces or all the individual components in the Hamiltonian could be understood or could be analyzed by this creation and destruction operator of a single particle. Therefore, you can count how many excitations or how many quasi-particles and what are the energies carried by this quasi-particles very easily. So this is the first, the trivial example of the Hamiltonian of a free electron in the presence of a single particle scattering. Okay, so later we will analyze this Hamiltonian mostly in K-space and by counting electron number and so on. So let's take a short break. When we come back, we will officially introduce these two body Coulomb-like potential in many body states. Let's introduce this two particle operator, which is Coulomb-like interactions. So we know very well that these Coulomb interactions are present in all the solid state materials, and this is the most important piece of the Hamiltonian that we need to analyze in this course. So imagine that we have many electrons in real space I and J or in any different quantum states, and they could interact with each other. And Catone picture is the this kind of scattering. So electron number 1 and number 2 carry different, say, momentum, and when they get scattered by Coulomb interactions, and the final states are two different electrons carry different momentum, for example. Okay, but you can also understand this Coulomb interaction in real space, that two electrons are from different places and they get closer and they repelled by the Coulomb repulsive interactions and so on. And we could define again this matrix element of this two body potentials in the occupation number basis that we already defined previously. So this mu and mu prime stands for the occupation number representation of a many electron or a many fermion states. And this is, again, given by the product of many single particle wave functions, say in real space. As we already derived for the single particle potential term, but this is the two particle potential. It involves 4 states, 2 initials and 2 final. So again, each of the initial and final many electron wave functions is made of the product of all these single particle wave functions like this. Okay, and you know very well that this matrix element involves only the electron states and Ri and Rj and nothing else. Okay, or this alpha I and Ri. So let me finish this and we take a short break. So U I star Ri and U J star Rj and U Z Rn. Okay, and same for the this initial states. So it involves U A R1, U I Ri prime, and U J prime Rj, and U Z prime Rn. Okay, so in other words, this potential connect this states of electron Ri and Rj, right? And therefore only 4 states are involved. 2 initial states, Ui prime Ri and Uj prime Rj, and also 2 final states, Ui start Ri and Uj start Rj. Okay, and it is independent of any other particles. So it involves only 4 states, 2 initials and 2 finals, and nothing else. Okay, so let's take a short break. When we come back, we will continue deriving this second quantized formulation of the 2 particle Coulomb interactions. Okay, so let's continue. As I define here, the matrix element for a 2 particle Coulomb-like scattering is defined by this following integral, say in this Schrödinger picture. But we know that each of this particle could be represented by second quantized fields and operators, and this many electron wave functions can be decomposed in terms of this product of this many single particle wave functions, and each of the single particle wave function can be represented by a creation operator. And this 2-body interaction only involve 2 initial states and 2 final states, and the remaining part of this single particle wave functions are decoupled because this orthonormal conditions for all the other single particle wave functions from quantum mechanics. Okay, so you got a bunch of delta functions, delta AA prime, which is the orthonormal condition for state A at R1 and state B at R2. It's the same thing for this delta function to arise, and so on and so forth. You get many delta functions which decouple this matrix element, and this matrix element only involves 4 states, as I mentioned, 2 initials, gamma and delta, and 2 finals, alpha and beta. Okay, so you could use the same way to define this 4 states, 2 initial and 2 finals, as the destruction of 2 initial particles, and you create 2 final state particles. All right, so using the cartoon picture, this is the plot that you could think of this 2-body interactions that have 2 initial states come in carrying quantum number gamma and delta, and into the scattering center. And after scattering, 2 new particles are created carrying quantum number alpha and beta. Okay, in other words, you destroy 2 initial particles and you create new particles. Okay, so we could generalize this way of interpreting this single particle wave functions in terms of a single particle creation destruction operator. It's just we have more complicated terms, like we have 2 daggers and 2 non-dagger, and we know that this C and C dagger operator satisfies any commutation rules that we already mentioned. So later we will interpret this alpha and beta and gamma and delta in both real space or in momentum space representation. Okay, so we could consider to create or destroy a single particle either in real space coordinate or in momentum space. Okay, in other words, we could create electrons here in real space, Ri, or we could destroy electrons in momentum space K. Either way, okay? And the operators in real space and momentum space are related by a Fourier transformations, and we will discuss that relation in just a moment. Okay, so let us just perform a very simple consistency check, meaning I can imagine, say, Coulomb potential is not 1 over R potential, but just a constant 1. So this is just artificial, but this kind of very simple, naive form of a potential allows us to check the second quantized representation of this potential reproduces the very simple constant potential that we could simply get the answers without any fancy second quantized fields, because if VRI minus RJ is simply just a constant 1, meaning we have a constant potential energy between any 2 of these particles, and this total potential energy is nothing but sum of these pairs of these electrons, right? So each of the pair of electrons has the same potential energy, 1. So you simply just sum of all these pairs of electrons, and each pair of electrons interact by a constant energy 1, and so you got a bunch of 1 plus 1 plus 1 plus 1 up to m different particles, and at the end of the day, this is nothing but n times n minus 1, right? Where n is the total number of your electron particles, and divided by 1/2, and this 1/2 here is to guarantee there's no double counting here. Okay, so you count all different particles I and j. I and j are different particles, and you count how many pairs are there, and each pair costs energy 1, and you sum of all this 1. And how many 1s are there? Well, there's n times n minus 1, that many pairs, and you divide it by 2, and this is your total energy. Okay, it's naive looking, right? Good. So we know the answer, but the non-trivial thing is that we could redo this calculation in a more fancy way, that we defined this potential for 2 body interactions in terms of the C and C daggers, and we take advantage of this any commutations for Fermion operators, and we could check exactly that this type of definition for 2 body interaction, second quantized form, exactly reproduce the same potential energy if we simply choose this potential between any 2 pair of electrons is just 1. And this check is non-trivial, so let's do the check. So as I mentioned, this matrix element V alpha beta gamma delta involves 2 initial states, gamma and delta, and 2 final states, alpha and beta. Right? So in a very naive form of this constant 1 potential, and this potential energy is simply just 1. All right? And therefore, this matrix element V alpha beta gamma delta becomes very, very simple, because you could take advantage of this orthonormal condition for a single electron wave functions. right? So you get two delta functions, one by this, another this. Okay, and you integrate over the real space vector dr1 and dr2, when r1 and r2 are independent integral over spatial coordinates. So you get delta alpha delta and delta beta gamma. So remember, delta function is a function that gives you either 1 or 0. 1 is when I equals j, and 0 if they are not the same. So this indices alpha, beta, gamma, delta could be the same quantum number or could be different. For example, if they are representing, say, spin, so alpha, beta, gamma, delta could be spin up or down. So, you could have all spin up or all spin down, or some up and some down, spin stays, and so on and so forth. Okay? So you simply just plug in this result matrix element, these two delta functions, back to the operator over there, and then perform the summation over alpha, beta, gamma, delta. And the way that you can simplify this is to take advantage of the anti-commutation rules between two Fermion operators. Okay, so first let's just sum over two of its four indices, say gamma and delta. So gamma, I let gamma to be the same as beta, and delta is the same as alpha. So I get rid of this gamma and delta. So by assigning this gamma to be beta and delta to be alpha. So gamma and delta are gone, so the remaining summation is over alpha and beta, so you get C dagger alpha, C dagger beta, C beta, C alpha. And this summation could be done if again apply this anti-commutation rule. So first, let's just switch the order between C beta, C alpha. So if I interchange these two operators, because this is just a destruction operators, and when I switch, I get a minus sign, right? So now I could just take advantage of this anti-commutations. I can simply just rewrite this C dagger beta, C alpha as the C alpha, C dagger beta subtracted by a delta alpha beta, and you could simply just use this identity to replace this C dagger beta, C alpha by this stuff in the bracket because of this anti-commutation rules. Remember, this is C alpha, C dagger beta plus C dagger beta, C alpha. All right? So therefore, C dagger beta, C alpha is delta alpha beta minus C alpha, C dagger beta, but there is a minus sign here, so it cancels, so you get this term. Then I could just expand these two terms, and I get the following term. So the first term is sum over alpha beta, C dagger alpha, C alpha, C dagger beta, C beta. Remember, this is nothing but a number operator, right? And alpha and n beta. And the second term is the delta function. So you sum over this beta, and you get beta equals to alpha. So this is C dagger alpha, C alpha. Okay? So you simply just plug in the definition of this number operator. Here, for fermions, for electrons, it's nothing but 0, 1 for n alpha and n beta, because n alpha and n beta are nothing but the occupation for these fermions in state alpha beta, and this can be either 0 or 1. And you sum over all possible alpha and beta, you get exactly 1/2 n times n minus 1. So magically, this matches this naive counting of pairs of electrons without employing this complicated second quantization. But this is just a trivial case, right? So you could simply just, without employing this second quantization, and you know this potential energy. But in a more complicated case, for example, the Coulomb potential, which is not constant anymore, then you cannot simply just perform such a simple, naive calculations. You need to rely on the second quantized representation of the operator. And this is telling you that no matter how simple or how complicated your potential energy is, you can always rely on the second quantized formulation because it reproduces this naive, simple limit of this potential. All right? So this just tells you that complicated calculations reproduces the simple limit, but in the more complicated case, you don't have that simple calculation available anymore, that you need to rely on this more complicated second quantized representation of this operator. Okay? So now you should appreciate this power and magic of these anti-commutations and number operators, so that you could really, sum over all this kind of number operator and use in this anti-commutation relation to simplify this calculation, right? Good. So let's erase the blackboard, and when we come back, we will continue to introduce the Fourier transformation or relation between the real space and momentum space operators in second quantized form. Yeah.
如果说我们真的采用这种 second quantization 的方法，我们真的在计算线面端生产的时候，会需要的那个应该怎么讲？就是 matrix 的 dimension 会降低到多少程度？就是说实际上这种方法是能够加速多快这种数据运算
Well, good. The answer is that this is the only way. There's no other way. And how efficient is this? Well, it can be very efficient for simple cases like Coulomb interactions in the mean field, approximation. Okay, so you don't need to diagonalize a very big matrix. Okay, so we will see later that for a non-interacting electron gas, it's just a 1-by-1 matrix. And for Coulomb interactions, well, you need to do some approximations. Okay, so it doesn't involve a large matrix diagonalization. Okay, and in the case of superconductors, okay, the BCS theory of a superconductivity, it involves only a diagonalization of a 2-by-2 matrix in K space. Okay, well, this approach, of course, if you really want to solve this eigenfunction of each individual electrons, you need to employ so-called density functional theory, meaning that you need to really solve for the Schrödinger equation under certain approximations, okay, and using the second quantized form, of course. And to that regard, of course, it is really time-consuming job, right? If you really want to calculate all this wave function of molecules and electrons. But if you don't care about that, but just focusing on the low temperature, low energy limits of your electronic states, okay? And you don't need to deal with millions of electron wave functions. You need only to count the number of your quasi-particles. So in that regard, it doesn't cost you any time to calculate numerically, okay? Why? Because remember, we have this Fermi-Dirac, right? Right. So at zero temperature, it's just step function. And if you can rewrite the Hamiltonian in terms of the occupation number, then you are done. Okay? So I emphasize millions times the power and magic of this occupation is that you can rewrite this Hamiltonian in terms of occupation. You know this is Fermi-Dirac, and you are done. As simple as that. You got it? No magic. And this is the only way that you know the lower energy properties of a solid state, is you could re-express the Hamiltonian in terms of the number operator. You know what this is, and therefore, in principle, this problem can be solved. Okay? So without solving the millions of Schrödinger equations, you only need to count a handful of quasi-particles at low temperatures. So you completely get the picture, and this is the only way, no other way. Okay? So the density functional or the first principle approach that I just told you, of course, is another way, but the drawback of this density functional theory is that it is the black box. Okay, so you put you put all this position of the atoms and electrons and their parameters and so on into the black box, and you minimize the energy, and you find the optimal, wave function that minimizes your energy, and you get the band structure, electronic band structures. Okay, so that's one other way. But you don't know exactly what's going on inside the black box once you find some interesting features. Okay, so for example, you notice some very interesting quantum phenomena out of the band structure, but you don't know what is responsible for such a phenomena. So what is the most important couplings in your system that give rise to such a phenomena? You just know the band structure and that's it. But if you can rewrite this Hamiltonian in terms of the second quantized fields, in terms of number operators, at least you have a feeling. Of course, we are not solving the problem exactly, but up to very high accuracy, we know the most important physics without solving the 10 to the 23rd that many atoms and in Schrodinger equations, right? Good question. So you will appreciate this formulation more and more once we start to calculate something. Great. So let's try to again relate this real space and momentum space formulation of the second quantized fields. And okay, remember we could define this operator, destruction operators, in any orthogonal normalized eigenbasis that we can think of in quantum mechanics. Namely, if we destroy a Dirac-Broglie state K, where K is anything, any quantum number, and we create the empty states, and therefore we could call this we destroyed a particle. And I use this as A operator, nu, where nu is simply equal to K, where K is some quantum number, labeling this quantum states. But we could also define the destruction operator in real space, meaning I could destroy the particle here in position R by destroying this Dirac-Broglie state R in real space representation and create empty states. Okay, so this K could be momentum eigenstates, and R is a real space coordinate. So, for example, if I consider electrons in a non-interacting electron gas, so all the electrons are occupied at zero temperature below the Fermi surface, right? Okay, so I can imagine that I could destroy the single electron occupied states, which I call this K. Okay, I could simply just destroy it. But do I know where this electron is in quantum mechanics if we know the state K in momentum space? Do we know where this particle is in real space? This is a quantum mechanical problem. So at the level of your undergraduate introduction to quantum mechanics, you should be able to answer these questions. So tell me the answer. If we know a particle exactly the momentum state in momentum space, do we know where the particle is in real space location? Following quantum mechanics. Yes or no? There is just simple answer, yes or no. And why, of course. So let's take a poll. If you say yes, please raise your hand. Yes means that we could know the momentum and position of a quantum particle simultaneously at the same time. Okay? And no means we do not know where the particle is if we know exactly the momentum of that particle. So, of course, the answer is no. But why? Tell me why. So there's a very fundamental principle in quantum mechanics that explains why. And vice versa. If we know exactly the particle position and we do not know the momentum of that quantum particle, because there's a very fundamental principle called what principle? Let me ask some of you to answer that questions. So there's not many principles in quantum mechanics. There's a Pauli principle, but there's more fundamental principle than a Pauli principle. But everybody should know when you learned quantum physics or modern physics or even general physics in your freshman year, the first year, or even high school, you know that. What principle is the most important principle in quantum mechanics? It's called what principle? Certainty principle. Who proposed such a principle? Who is the great physicist who proposed such a uncertainty principle? There are not many physicists, in the 20th century who built this quantum mechanics. So, what uncertainty principle? There's a name, right? There is a gentleman. So you don't forget your quantum mechanics, Heisenberg. So the Heisenberg uncertainty principle tells you that the uncertainty of measuring the momentum of a quantum particle times the uncertainty to determine the position of the quantum particle as a lower bound is greater than or equal to 1/2 h bar, meaning you cannot know exactly the momentum with 100% accuracy at the same time and know the position of the quantum particle 100% in accuracy. Because delta x times delta p is positive, is non-zero, is greater than 0, and is greater than 1/2 h bar. Okay? And which means that if you know the quantum particle in state k in momentum space, and you certainly don't know where they are. All right? And likewise, if you destroy a quantum particle in spatial location r, and do you know the momentum associated with that quantum particle exactly? Of course not. So these two destruction or creation operators in different eigenbases are sort of orthogonal to each other. Okay, but it's equally important and meaningful to define destruction or creation operator in either space. You could destroy a particle, create a particle in real space, but you don't know the momentum variables. And likewise, you could destroy the created particle in k space, but you don't know where they are. But I could equally well destroy a particle either in real space or in momentum space. And sometimes it's more convenient to destroy than create a particle in real space, and sometimes in momentum space, either way. So I have the freedom to destroy it or to create a particle either in real space or in momentum space, whatever I want, whatever I need. However, there is a relation between these two. So tell me, what is the relation between these two? So I already wrote down the relation. Okay, anyone know the relation between the real space and momentum space operators? It's already somewhere here. So what is the relation between these two? When you learn this Heisenberg uncertainty principles, you must know that there is a relation between real space wave function and momentum space wave function, right? Okay, so they differ exactly by a Fourier transform. Yes? Now your memory is back. That's good. Because we are not doing something fancy, because we go back to quantum mechanics that real space and momentum space wave function, they differ by a Fourier transformation. And likewise, the creation destruction operators defined in real space, in momentum space, they differ by exactly Fourier transform. Okay? And so this is nothing but the relation between the real space Schrödinger wave function and momentum space wave functions in quantum mechanics. Good. So let's just try to write down officially the relation between these two. So if I define this creation operator in real space, and I could decompose this operator in terms of any other orthonormal basis, and I can choose this basis to be the momentum space. So if I define my nu as momentum eigenstates, and my R is what? The position space, right? And there is a Fourier decomposition of a Schrödinger wave function in terms of the linear combination of a momentum space wave function, right? And you could simply just consider this as your Schrödinger wave function. It's nothing but the Fourier integral of your momentum space wave functions, 5k times e to the ik dot r, and you integrate over dk. Okay, so this is from your quantum mechanics. You know that the Schrödinger wave function in real space could be rewritten in terms of the Fourier integral over the momentum space wave function, right? Phi of k. And this is precisely the situation here, that this corresponds to the Schrödinger wave functions in first quantization. So we will come back to this just a moment. Likewise, you could define your destruction operator in real space and rewrite this in terms of Fourier integral over momentum space. And this coefficient here, psi nu of r, is nothing but the, this momentum space wave function. This one. This is your psi k of r. Remember, for free particles in quantum mechanics, the wave function is actually the plane wave e to the ik dot r, and this plane wave function is also the eigenfunction of the momentum operator, right? Okay, and which is precisely the coefficient here. So derive some important relations of these two different operators defining two different eigenbases. So define my operator C or A in momentum space, and they satisfy the anti-commutation rules. Okay, so if you simply just define your operator in real space, then you should satisfy similar anti-commutation rules. Similar, I mean, they should be equivalent, but mathematically they have slightly different. I delta Rj delta Ri minus Rj. So the only difference in mathematical form is the difference between the Kronecker delta function and Dirac delta function. Delta k prime 1 over 0, but delta Ri minus Rj is that this is either infinity Ri plus Rj or 0, and if you sum over the real space of this delta function, it is 1, meaning this Dirac delta function is actually giving you infinity when this argument inside the bracket is 0, meaning when Ri equals to Rj, so delta 0 is actually infinity. But this peak is actually a sharp spike where the height is infinity, but the width is 0, almost 0, so that the height of this Dirac delta function goes to infinity, and the width goes to 0. So if you integrate over the entire real space over the Dirac delta function, it gives you 1, because you get the infinitely high peak but infinitely narrow width, and the amount of the infinity in height actually exactly cancel the infinitesimal narrow window approaching 0. So it is something like x goes to 0 in the denominator for the height, but x goes to 0 of the width. And if you multiply this two, 1 over x times x, you get exactly 1. And this is how you get this unit when you integrate over the Dirac delta function in real space. All right? So, but the Kronecker delta function is just a step function. It reports to you 1 if they are the same. If they are not the same, it is 0. So it's either 1 or 0. So the step function is not delta peak. Okay? So it's either 1 or 0. But the Dirac delta function is either 0 or infinity. So now comes the homework. So the homework is that using this Fourier transformation between the real space and momentum space, and you can prove that the destruction and creation operator in real space satisfy the similar but not exactly the same in mathematical formalism that this psi dagger anti-commutator reports to you the Dirac delta function, not the Kronecker delta function. So the useful identity is this. When you Fourier transform any wave functions, it involves such a summation over this Fourier coefficient e to the I k dot r, and if you sum over k over e to the I k dot r, you get Dirac delta function. All right, so this is the only identity you need, and therefore let me just write down the operator in R and K space. So they differ by a Fourier decomposition and a dagger of K, the R, K dot R, psi dagger R. Okay, so in other words, the A dagger of K and psi dagger of R, they could be transformed to one another by a Fourier sum or Fourier integral. And the Fourier integral is defined here that link A, K, and psi of R. All right? So if you know the anti-commutations for AK and AK dagger, you must know the anti-commutation for psi of R by this Fourier relations, and you could use that advantage to show that this real space operators satisfy these anti-commutations if they are fermions. All right? Okay, good. So that's enough for today.